Hello everyone, thank you for attending our talk. It's a pleasure to share our research on Wi-Fi security with you. Today we'll be talking about Wi-Fi attack surface and how to find high-risk vulnerabilities in Wi-Fi driver. First of all, allow me to introduce my partner and myself. My name is Xie Haikuo. I'm a security researcher from Huawei Singularity Security Lab, and my main research field is software vulnerability. Wang Ying and Zhang Ye are security researchers of Baidu Security Lab. They are good at finding and hacking IoT devices. Next, Wang Ying and I will show you this topic. Let's start our topic. This is an overview of today's presentation. We'll start with introducing some mainstream Wi-Fi chip manufacturers in the world and the Wi-Fi vulnerabilities in recent years, so that you can have a general idea of the Wi-Fi devices we use and their current security status. Then we'll move on to some key attack surfaces of Wi-Fi. In the end, I will explain our vulnerability discovery methods and share two vulnerability cases. Without further ado, let's begin with the background. Wi-Fi technology has been around for more than 20 years. Most of the Wi-Fi chips used by smart devices today are produced by Broadcom, Qualcomm, Realtek, MediaTek, Marvell, and Intel. The famous products that use Broadcom Wi-Fi chip are Apple Computer, iPhone, and Samsung mobile phone. Qualcomm Snapdragon mobile platform is widely used in today's Android phones. Intel Wi-Fi chips are mainly used in laptop computer, in which Lenovo and Dell laptops use Intel Wireless Network Adapter. MediaTek Wi-Fi chips are used in router, network adapter, and Android phones. Realtek Wi-Fi chips are mainly used in routers and USB network adapter. The most popular USB wireless network adapter in China use Realtek Wi-Fi chips. Marvell, Microsoft Surface Pro use Marvell Wi-Fi chip. No technology is born perfect. History shows that Wi-Fi also has many vulnerabilities. Even after more than 20 years of development, its security remains to be a big concern. In 2017, the remotely exportable vulnerability of Broadcom chip exposed by Google Project Zero team compress Android and iOS as long as the attacker and the target device are in the same Wi-Fi network. They can launch the user-insensitive attack. In 2018, Dennis introduced a remote vulnerability exploitation of Marvell Wi-Fi chip at the ZeroNet conference, which is also an attack that can be launched without authentication. In 2019, US CERT released a number of security alerts for Broadcom Wi-Fi chip drivers, which affected Android, Linux, routers, and other devices. I also read the attackers can launch attacks through malicious Wi-Fi packets. These attacks can be launched without authentication, no user interaction is required, and no physical contact is required. For ordinary users, this kind of attack is very difficult to prevent. Is the reality really so bad, or are these just individual cases? To get to the bottom of this, we took a closer look on Wi-Fi security and found that this is actually a big attack surface. Next, we'll focus on key attack surface of Wi-Fi. Wi-Fi chip is used in intelligent devices. It not only sends and receives communication packets from data link layer, but also interacts with system and software. The communication interface and operating logic of data link layer have remote attack surface. The finger on the left lists several remote attack surfaces with great influence. The finger on the right shows the local attack surface of Wi-Fi. The software can communicate with Wi-Fi driver through L control interface of Wi-Fi driver. Because the code is in the kernel driver, the code running authority is very high. If there is a vulnerability, it can cause local probability escalation. Well, we mainly focus on the remote attack surface. First, let's talk about the association stage. The three interactions of station associating access point. This is the most basic and widely used function of Wi-Fi. Access point refer to wireless router and other devices that generate Wi-Fi hotspot. Station refer to mobile phones or computers and other devices connected to Wi-Fi. How does a mobile device access the wireless network? The connection of wired network is very simple. As long as the network cable of the device is inserted into the network port, the network system is connected to the wireless network. Need to complete this part of work through the management frame. The mobile device search the network system. The network system verify the mobile device. Finally, the mobile device is associated with the network system. Then the wireless network system is connected. The above function is mainly implemented by management frames, such as beacon frame, prop frame, authentication frame, association frame, etc. This page takes the structure of association request frame as an example to introduce the structure of a management frame. The management frame is composed of frame handler and frame body. The frame handler contains the MAC address of target device and the source device. The frame body is mainly composed of information element. The structure of information elements is a typical TLV structure, tag length value. It usually contains a byte element ID field, a byte length field, and a variable length value field. Some information elements also have an extended element ID field. More complication in the more dangerous. However, in the process of station accessing access point, only 3 message interchange. What is the complexity of such a simple process? The complexity lies in the information element. First, a variable length structure. Generally, there is a standard range for the length of an information element, such as SSID information element, which is usually 0 to 32 bytes, but the actual value of this structure can reach 255 bytes. If the length is not verified in the driver, it's easy to cause buffer overflow. This kind of vulnerability is easy to find, but even if it was found more than 10 years ago, that doesn't mean you won't make the same mistake. Second, there are more than 200 kinds of information elements. An information element carries a kind of information. It must be a lot of effort for coder to implement these functions. It's because of the abundant information elements that Wi-Fi boasts such rich features and functions, which also expand its attack surface. Third, the extensible interface for the future is reserved in the information element, and the operation of the extended information also increases the complexity of the program, which also increases the security risk. In the vulnerability cases later, we will give an example to illustrate the risk brought by this operation. Fourth, private customized information element. Vendor-specific information element can not only contain the content defined by each manufacturer, but also include the Wi-Fi protection access and other functions. It carries so many functions in an information element, which requires a higher level of information element passing. Fifth, structure contains structure. Taking as an information element as an example, as it represents robust security network. The information element enables station and access point to exchange security information. It contains encryption suite supported by devices. The encryption suite has a count field and the corresponding suite list. It may cause conflicts between the length of information element and the count field, which can easily cause problem. All of these are challenges for coders, not to machine some undefined parts in the 102.11 specification. They even create infinite possibilities. Wi-Fi authentication stage. This doesn't refer to the part of the interaction of authentication frame, but the actual verification of the password information of station device. Other authentication methods such as WP2 is the four-way handshake of EAPOL package. The more complex one is the eight-way handshake authentication of WPS, and the more complex is the authentication of enterprise WPA. This stage involves more computation of cryptography algorithms, and attacks based on algorithmic vulnerabilities usually occur at this stage. For example, KRACK vulnerability. Of course, there is also the possibility of memory corruption vulnerability. Wi-Fi also has many other functions and features, such as spectrum management, TDLS, radio measurement, fast BSS transition, and so on, which can be well researched. Next, I'm going to introduce our vulnerability discovery method, a black box protocol value. It's based on 802.11 specification, so we can use it to find Wi-Fi model of different manufacturers on different operating systems. This is our fuzz process. In fuzz mode part, choose our fuzzing target, such as access point, station, P2P. Then the fuzzer will mutate frames with special mutation strategy and send the frames to target devices. If detected a crash, we will try to generate POC and analyze vulnerability. We designed three fuzz modes, including access point mode, station mode, and P2P mode. In access point mode, our fuzzer is a fake access point which interacts with the real station device. In station mode, our fuzzer is a fake station which interacts with real access point. In P2P mode, our fuzzer is a fake P2P device which interacts with real device. All of these three modes cover the pre-machined remote attack surface. In our opinion, the efficiency of fuzz is significantly affected by the quantity of mutation strategy. Our mutation strategy is the primary reason that we can find out some vulnerabilities. To start, we tested a target device just through a laptop and a wireless network adapter. Many vulnerabilities were found within 10 minutes, and the remaining bugs were found within several hours. The dynamic mutation degree in the left graph acts the 3 times of mutation strategies in the right graph, which make our mutation strategy more flexible and can be tested both widely and deeply. By saying management frame mutation, we mean management frames are sent in an ordered or unordered manner. By saying information element mutation, we mean we will combine various information elements in an orderly or disorderly way to create a malformed management frame. By saying mutation of information element content, we mean some fields of information elements are mutated and a malformed information element is generated. Now, I would like to show you how to mutate management frames during the interaction with an example. The first method is to send the management frames according to the normal logic of Wi-Fi. As shown in the figure, we can mutate probe request or mutate probe request and association request. In this way, following the state machine, the deeper logic can be tested. The second method is to send the management frame, control frame, and date frame randomly. Different combination of management frame and control frame may trigger new code paths. Next, we will talk about information element mutation. Take association request as an example. As we know, frame body is mainly composed of information elements. So we can mutate the frame by adding information elements, changing information elements, or deleting information elements. Lastly, we'll talk about mutation of information element content. Take the ISN information element as an example. We can see that information element is composed of various fields. We set a group cipher OUI with a random value and give pairwise cipher suit type a random value. So this information element becomes abnormal. Now, I will hand it over to my beautiful partner, Wang Yi. She will go on to introduce the following slides.
After the frame mutation, we need to send them to the target. The A02.11 protocol is at the data link layer. We can use the monitor mode of the wireless network adapter to send the communication packet at the data link layer. The command on the right graph is to set the network card to be monitor mode and set the channel. We have tried these three schemes to send frames, each with its own advantages and disadvantages. The rail link has the advantages of the no prices and the stable performance. The disadvantage is that the timestamp field can't be set, but it doesn't seem to affect sending frames. The AR9271 network card can ensure the content of the package is completely controllable, but the monitor mode is not stable and it often be stuck. The advantage of SDR is that the sending frame is fast and the content is controllable, and disadvantage is that the cost is too high. Regardless of the varieties of Wi-Fi devices from different manufacturers and platforms, we can send frames through network adapter and fast. However, things goes easier in Linux. We can communicate with Wi-Fi module without wireless network card by modifying source code. As shown in the figure, firstly, we create a queue in the kernel. Then a program in the user layer keeps input the multiple frames into the queue. Whenever the kernel layer receives an external frames, it will take out a malfault frames from the queue to replace the external frame. So the Wi-Fi module in kernel will purge the multitate frames like the picture on the right. The advantage of this way is that it can improve the efficiency of fuzzing and ignore the influence of the wireless network adapter. If we find a crash and then POC streaming is completed, it is necessary to analyze the cause of the vulnerability through reversing binary file. In most cases, we don't have the driver source code and can only analyze vulnerability by reversing binary file. Generally speaking, the latest driver does not have symbol information. We can only search for the symbol information of the old version on the internet, which is also very helpful to us. Also, we can use the IDA script to restore the function names in the benches, because some streams contain function names or related information. Finally, we are able to analyze vulnerabilities by binary symbol information and the function stack after system crash. In half a year, we discovered 18 Wi-Fi 0-day vulnerabilities, like the pictures. Now let's move on to the next session, vulnerabilities. Since most of the vulnerabilities we have discovered are still being fixed by the manufacturers, we can't disclose details of those. So what I'm going to introduce are the public known ones. Now I will introduce two vulnerabilities we found. This one is a stock buffer overflow in the Wi-Fi driver of USB wireless network adapter on Windows platform. This vulnerability can be triggered in AP and station mode. When the Windows platform opens the mobile hotspot through this network adapter or connecting with a fake hotspot will trigger this vulnerability. These two IAs are the main causes of the vulnerability. They present the data rate and the extended data rate, which is supported by the device. The Wireshark screenshot is normal, i.e., as you can see, it is usually 8 bytes in length and the vulnerability exists in the association part. Regardless of whether it is a request or a response, as long as the two malicious construct IAs are carried, the vulnerability can be triggered. Pseudocode is used here to show the logic of this vulnerability. This function is to parse supported rates IE and extended supported rates IE, and then copy all supported rates to the global variable. We can see the length check can be bypassed. The first if statement is to determine whether the length of the supported range IE exceeds 36. If we set it to be 36, it can bypass the first one and the second one if condition. And then we can set extended supported range beyond the normal range, which would trigger buffer overflow later.
This is the POC demo.
The vulnerability exists in the Intel Windows Wi-Fi driver. It is a memory out-of-band write vulnerability. When the Windows system shared a mobile hotspot through this network adapter, the attacker can trigger the vulnerability as soon as contacting with it, causing the system to be blue screen. We first discovered this vulnerability in the ThinkPad X240 notebook. This notebook used the Wi-Fi Li260 wireless network adapter. Currently, the Wi-Fi network adapter has been discontinued, and the ThinkPad X240 is also a very old notebook, so this vulnerability exists at least in 2014. After testing, it was found that this problem exists in the corresponding Windows drivers of the above-mentioned wireless network adapter of Intel, including the latest AX200 chip. The core of this vulnerability is supported operational classes IA. This IA is to declare the operation classes supported by station. The structure is not complicated. One byte in the information represent a class. Use code to identify this vulnerability logic. From the name of the function, we can know that the function is to process the channel list supported by the association frames. In this function, the function of util regulate class to channel list is called circling. The function writes 512 bytes to the blocks of memory each time and accumulated the memory address. When the number of calls is too many, it would cause the memory to write out bands. The number of times of this loop is determined by the length field of the supported operation class's information element. That is, they can be up to 255 times. This is obviously low check on the length field passed in from user.
This is the POC demo.
Now, to conclude our presentation, use the above-mentioned vulnerability when an attacker pretends to be a mobile phone or a computer and initiates a connection request to a hotspot. The payload sent will cause security damage to the kernel, resulting in the denial of service of the PC operating system. Nowadays, personal computer, mobile phone, and more IoT devices supported wireless network communication, and the security of their underlying communication protocol is extremely important. And the security research on this protocol has important value. Most of vulnerability we found were in the network access stage. In fact, there is still a lot of research fields in the authentication stage and other functions. Okay, thanks again for participating. I hope our sharing today is helpful to you guys.